finished was connected with, I just indicated that all representation, finite representation of the Lorentz group can be characterized by two numbers, right? So I wrote M, N, or I used, M over N2, and those numbers, integer, positive or zero, and dimension of this representation is M plus 1 over N plus 1. Right, and I indicated examples in the very end of the class. I indicated examples of simplest representation. So like 0, 0, this is scalar. So this representation corresponds trivial representation. It actually does not change under any Lorentz transformation. Then I wrote this one, and this is extremely important. So this is M0, N equal 1, and this is left-handed while fermions. It's like actually our neutrinos. Before people recognized that they could have masses, they actually left-handed, and they assigned to this representation. This representation, M1 and 0, and this is right-handed. I will explain later what does it mean right, left-handed. It's connected with polarization of spin with respect to momentum, but we will come to that, don't worry. And I indicated this case, 1/2, 1/2, and this is extremely important case. This is case of electron, proton, any massive particle with spin 1/2. This is Dirac equation connected with this representation, Dirac fermions. And, oh, sorry, this is absolutely wrong. Yeah. Okay, this is, of course, representation which describe photon field, and this is vector field. So this guy has 4 components like coordinate x, right? So it transforms like actually our x mu as x mu. So this is transformation, same like transformation of coordinate. And this is actually Dirac case. Sorry, it's bispinor, of course. Case, not irreducible, reducible representation because it's sum of 2 irreducible. And this is Dirac bispinor. So it describes electron, proton, so this is case. And so I stopped at the question, what describes gravity field, right? What is M N for gravity field? And this is, of course, symmetric tensor, you know, which depends on x. It's connected with metric, but metric different at different point, g mu x. So this is question. Okay, you see this guy, let's look at this representation. It describes vector, just one Lorentz index mu, which takes 0, 1, 2, 3, right? There are two. So it's quite convenient to consider, to come to this answer, tensor of second rank. So when we have two indices, and it corresponds to this representation when we take two of them and consider direct product of these two representation. Okay, this can be actually rewrite like this. This is same thing. And remember, as I said, those M and N connected very similar to those quantities which appear in representation of rotational group. Rotational group is characterized by angular momentum, right? So we have each representation has particular value of angular momentum. For example, spinor, right? This is 1/2. Or our usual vector in 3 dimensions, this is 1, right? And 3/2, 4, all of them. So we characterize by this one. And there is famous adding theorem for angular momentum. When we have this combination, which corresponds to direct product of two representation. So if we have, say, case rotational group, this is from quantum mechanics. So we have, in that case, J, say 1. This is one representation. And another one, J2. So this corresponds to set of the following rotational representation. This will look like that. So it will be J1 plus J2. And let's consider the case when J1 equal or larger than J2. So it will be J1, J2, J1 plus J2 minus 1. And up to the last smallest value will be J1 minus J2. This is all representation for rotational group from quantum mechanics, adding of angular momentum. So we can use same rule here. Okay, they are now equal. J1, J2, 1/2, 1/2. So we have actually, in this case, the largest one, and then next is 0, and we should stop, because no, of course, negative. So this, then what we have is this 1 and direct sum. This means just essentially independent. 1 and then 0. So 1 and 0, and same here. 1 and 0. So this is what we have in this case. Now let us again work out. We can, so this is still, we can rewrite, simplify a little bit. This is from, again, quantum mechanics. So you just consider that this guy is nothing else but 1. Let's consider all possible combination. 1, 1. And then I take 1, 0. And then I take 0, 1. And then I take 0, 0. So this tensor mu, how many components it has? 16, right? Because mu4 and nu4, we have 16 components, right? Okay. Now, let us understand those different irreducible representation we got. This we know. This is just actually scalar, right? And this scalar describes by trace T mu mu. Of course, when we consider sum over mu, we have scalar, right? So this is guy correspond to this stuff. Okay, now this combination 1, 1, it's actually, so this is one component only, right? We have one trace. Now 1, 1, this is symmetric, traceless part, which I will consider the following notation for this guy. And this guy is the following. So actually, you just take T mu nu plus T nu mu. This is symmetric part. We factorize in this case. Now we should actually remove trace. So minus 1/4 G mu nu and our friend T mu mu, because it's already used here. So this is guy, and this guy have actually, it's easy to calculate 9 components. Check this, it's quite easy. Okay, 9 components. So this guy plus this guy has 10, right? And also we have 2 others, 0, 1, 1, 0. And this guy corresponds anti-symmetric part. Okay, so we will write like that, T, and this is a kind of this symbol for anti-symmetric, and this is nothing else but we can write 1/2 T mu nu minus T nu mu. Of course, in this case, no need to subtract trace because trace of anti-symmetric equals 0, right? All diagonal equal 0. So this guy has 6 components. Okay, now what is physical meaning of all these things? First of all, calculate. We started from 16 component and we got 16. 1 plus 9, 10 plus 6, 16. So this is good. Okay, and now, okay, I put right here. Sorry.
Why is the second one is traceless?
Okay, point is that we want to pick up irreducible, which actually transform due to this MN classification, right? And look, we can pick up trace, and this guy 0, 0. So under Lorentz group, it stays separately from others because it does not mix with them. So we just call as it should be scalar, right? But because we already use it, we cannot consider double counting. right? So this is symmetric. There could be trace, but okay, this guy trace transform independently of all others 9 components. So it stays separately. You see, because of that 9, 1, 9, 10, and 6. Okay.
Why is there an emphasis on getting some irreducible representation?
Irreducible representation always are important in physics. So they correspond to a kind of special state, like, for example, angular momentum, right? If you have 1/2, there are 2 vectors, plus 1/2, minus 1/2. And you could consider separately from, say, angular momentum 1, because they never mix. You see, so irreducible representation is important because it can survive under group transformation just without mixing with anything else. So it's a kind of basic element of the group, right? Okay, now let us describe, first of all, gravity field. We can immediately say answer. You see, this is G mu nu, this guy, G mu nu, has 10 components. It's symmetric and it has trace. Because even in Minkowski flat space, trace is not 0, right? Because G mu nu is 1, minus 1, minus 1, minus 1. So we should include both. So we write G mu nu X, this famous Einstein, this construction, it corresponds to these 2 guys. So what is written here, right? So, sorry, trace plus this traceless symmetric part. Now, how about this guy? Antisymmetric. Is it irrelevant? No, it's actually very important. Not in gravity. So some people believe that actually it appears in modification of Einstein gravity. There is office of John Moffat in this Perimeter Institute, and he believes in that. Okay, so he has modification gravity theory in which, besides G mu nu, he used this antisymmetric combination, and he claims that he can describe everything, including dark matter, without dark matter. Okay, so this guy even potentially could be relevant for gravity. In string theory, it appears everywhere, this antisymmetric field. But it appears even in more familiar case, electrodynamics. So let's consider this. Example. And this is famous stress tensor. This is exactly this stuff. 3 electric component and 3 magnetic, 6. So this is exactly this guy. Okay? Now you could ask me why we consider for 0, 0, 1, 1 irreducible representation, but this guy is reducible. We have 2. Actually, you could consider in principle separately this and this. The answer is that there is, again, we do not have time to prove this. I already said this. Point is that if we compare 2 representations, NM and MN, then NM equal complex conjugation of MN. So you can see when those guys are equal, like 0, 0, 1, 1, this is real representation, right? M, M, oh, I should write, of course. Right, okay. Actually, right. Mm-hmm. When they are equal, real representation, right? But when they are not, they are complex. So point is 1, 0. This is 0, 1 complex conjugate. They are complex. But of course, this guy is real in electrodynamics. So we should consider them both to describe real 6-component electric field, magnetic field, right? So electric field, 3, and magnetic field. Okay, so this is examples. Maybe some more questions here. Just go ahead. Concerning this simplest and a kind of most important representation in physics, relativistic physics at least, representation of Lorentz group. Right.
What does that mean? I mean, E and B, you said that.
Okay, point is that in electrodynamics, you have electric field and magnetic field. So you have electric vector and magnetic vector. So this guy, maybe I should write, correspond to those through usual relation in electrodynamics. So they are here in this combination, electric and magnetic field, connected with vector potential in electrodynamics. It's called vector potential. Okay. So this is examples. Let's go further. Now, so we have, let's consider some general representation. 1/2 m, 1/2 n. And to this representation, we have matrix. I call this matrix connected with this representation. Say we consider this. And this guy, let me again connect it with this representation. So we have some vector, number of component m plus 1, n plus 1, like in linear algebra. We know the number. We already discussed this. It's connected with this representation. And for each Lorentz transformation, we have some matrix. And this is m plus 1 times n plus 1 matrix, right? So we have, this is square matrix, and this is each row and has m plus 1, n plus 1 elements, or maybe you can write. And column also has this number. For example, in 4 space, 4-dimensional, this is 1/2, 1/2. We have 4, actually we can write this. This is this matrix, right? 4 times 4 matrix. This is in general case, right? For 0, we have 1 to 1. So this is just not matrix, but number. Okay, so we have this, and under Lorentz transformation, what we have is this. Phi A goes to M A B for this transformation lambda, phi B. And of course, we always consider summation over repeated indices. We understand summation when we consider repeated indices. So examples, last time I considered boost and rotation in the case of four-dimensional representation, right? Okay. Now it's not the whole story, because actually we left outside, maybe in some sense, most fundamental four transformation. We consider here six: three rotation, right, transformation, and three boost, Lorentz. But there are translations, right? Okay, so let us consider this. Okay. Now, what I will discuss, this is inhomogeneous Lorentz group. There is better name, shorter at least, and justified. It's called Poincaré group. Poincaré, famous French mathematician, and he also worked in physics. Poincaré group. It's same. You can use both names. Okay, so let me describe inhomogeneous Lorentz group. By the way, quite short description of Lorentz group. I said that we will use this text, Peshkin, right? So it is in, let me write here. So this is essentially, but it's quite short description, Peshkin. He discussed this, but quite, it's short description. It's ours? Oh, okay, good. Okay, so we now should discuss inhomogeneous Lorentz group. Okay, so besides rotation and boost, there are, of course, space-time transformation. Which extremely important in relativistic field theory. This is very easy. X mu goes X prime mu, and this is X mu plus A mu. Some vector, constant vector, that's it. This is crucial, it's very important for sure, transformation, right? Okay, their generators, and I will show why. P mu, and this guy is four-dimensional gradient, if you want. So this partial derivative is I, and in more familiar way, I write like that. You see, this means when this, I told this already, index down in derivative, it means that you consider differentiation with respect to coordinate or time with upper. And upper, this is normal physical. This guy minus gets no minus here, space, because I put upper index, but this guy means that I'm considering a differentiation with respect to physical x, which has upper index, and then it corresponds actually this guy minus I and this index, lower index. Anyway, this is this. So those are familiar from quantum mechanics, of course. This is exactly what you write for operator connected with energy operator. And this is connected with momentum operator. Remember, Planck constant equal 1, right, in our units we use. Okay. Now let's consider finite translation. Not infinitesimal, I'm just right finite. So you should say just this operator minus AI, A mu, P mu. Okay, so you should, P mu is known, I wrote, and this guy acts like in order to produce this transformation. Let me show you. Okay, for example, this guy, I will be quite detailed here. Let's act on some phi of x. It could be just x, but I'm considering general case. Substitute this stuff, that this guy is this. So we have then A mu, D mu, phi x. Now it's good idea to consider, like, you can always rewrite A mu with upper, but this is with lower. This corresponds to this. So this consider differentiation of x and t with upper, with physical, phi x. Now let's consider Taylor expansion of this exponent operator. So this is 1 plus A mu D mu plus and so on plus 1 n factorial and A mu D mu n plus and so on. So infinite number. And it acts on phi x. And this is nothing else as fx plus a, because it's exactly when you consider Taylor expansion of phi at point a equals 0, you will get exactly this answer on the left-hand side here. Okay? So we now know how this guy acts. Okay, so has I used all? Right, so I use this. It's better for you to still consider. Let me consider here. Okay. This really simple operator, and because it's of course easy to check that if we consider commutator p mu, it's always 0, because derivatives, of course, they commute with each other. This is famous rule in calculus, right? That order of derivation is irrelevant, right, for partial derivative. It is abelian group. Let me write an abelian group. Point is, abelian actually algebra which Lie algebra, right? Which corresponds abelianly, right? Corresponds to abelian group. You see, algebra, this is manipulation with generators. Group, this is working with those exponential elements. This is element of group. We consider product of those guys. Here in abelian algebra, we consider their linear combination with real numbers and also commutators. This is Lie algebra. So abelian group means very simple. So the order, when I considering this, A mu, P mu, multiply to generators. Another one, which is B mu, P mu. It's equal, again, the order is irrelevant here. It's not correct in the case of rotation and boost, but this is much simpler. Theorem of mathematics say that all irreducible representation of abelian group, of any abelian group, are one-dimensional. Very simple, one-dimensional. Okay. So it's a kind of paradise when in the end of solving complicated problem, you reduce initial symmetry to abelian. It's very simple to work with. Actually, recently, I was involved with my collaborator studying by using actually relativistic language, quite hot topic in condensed matter, graphene. And we just showed that in the case of Hall effect, it's published Physical Review B recently. B, it's condensed matter. Actually, when you completely spontaneously break initial symmetry, it's U4. In that case, to just U1, you completely leave degeneracy of all levels and you get right whole plateaus and so on. So abelian case is simple. It's easy to work with. So all irreducible representation are one-dimensional. Let me describe in this case. Okay. Okay, so what we actually have, let me take phi x in this case, right, to be equal this one. So just plain wave. Remember this guy, this is Lorentz summation. We have time here and spatial component. Plane wave. Then act on this particular phi, this our operator. It acts on this. And we know answer that it's x plus a, right? So we have this. Okay, let me write again here. Okay, anyway, it seems clear. Then we have A mu plus X mu. And I could write this as product. Times initial So you see, this guy's eigenvalue and this guy plane wave eigenfunction. And because we can pick up arbitrary k for this operator, the spectrum of the eigenvalues is continuous, right? Like because you can take any k between -infinite and +infinite. So it's like in quantum mechanics, right? And it's not surprising because those operators is energy and momentum, and we know that in quantum mechanics, plane wave are eigenvalues of them. So we have huge number of different one-dimensional irreducible representation, but infinite number, right? So this is description of translation group, very simple. Okay. But now, what is called Poincare group. Now we should add some questions here. Go ahead. Yeah, please.
Here, why changed in how did this one? I mean,
This one?
Yeah.
Look, this is just usual noun numbers, right? We know the property of exponent. Right?
Yeah.
So I use this.
Because here.
Oh, this.
A,
Oh, okay. Look here. Look here. What we got?
Oh.
Acting on phi x, you got phi x plus a. But I did the same. This guy acts on this and gives x plus a.
Oh, yeah.
That's it. So it's same like written here, right? Other questions, don't hesitate. I'm available.
So classically, how are we identifying the P mu as a generator?
Okay, P mu is written here. P mu is generator because this is derivatives, right? Like graph. So derivative acts on function. Because of that, it's called operator. Like in quantum mechanics. In quantum mechanics, there is operator of momentum. And this is nothing else but this, minus I graph.
Yeah, but if you leave quantum mechanics out.
Why we should out? Quantum mechanics is good. Quantum mechanics, from mathematical point of view, this is theory of operators. Nothing else from mathematical point of view. There is much more from physical point of view. But we have just theory of operators actually in the Hilbert space, so-called. So this is the same. We certainly can use it. So certainly those guys are operator because we know how derivative acts on function. It yields its derivative, and this is different function. And by definition, what is operator? Operator, something which acts on function and could give different functions. That's it. Good. So quantum mechanics with us. Don't touch. Right.
You don't necessarily need quantum, right? Because you can say
Sure.
if P is your conjugate
Right.
to X, and then you
E-
can use
exact-
you can use Fourier analysis.
Exactly, exactly. But you know, I assume that all of you took the course of quantum mechanics, and language of quantum mechanics is more familiar. But you are absolutely right. It's purely mathematical problem. Description of translation. And you, of course, could consider classical even quantities, right? Like in electrodynamics. And you could describe this symmetry by using these operators. Absolutely. Just it's more familiar. But you are right, of course. Okay. Now, what is Poincare group? To get Poincare group, we should add those 6 Lorentz generators and those 4. We will get 10. And it's not so simple group. And it acts wonderfully, actually, in quantum field theory. And it actually even could, oh, we can use this, right? It actually solves some important problem, the use of it. Okay. Poincare group. So start Poincare algebra Lie, or Lie algebra. It includes those generators, P mu we just discussed, and J mu nu we discussed 6 of them because it's antisymmetric. So we should consider known commutation relation between what we already learned with you this is I already wrote, but let me be generous and write it again. And remember, typos are inevitable, so just stop me.
Yeah.
Yeah.
Change that to G mu rho sigma.
The first one.
Oh, the first one here?
In your conjugate, yeah. You have
Oh, sure. You see, I even was blind. I looked and said, where? Yeah, exactly. It's remarkable. Mu nu. And this sigma rho, I believe. Rho sigma, right, exactly. Thank you so much. Yeah. Because it will lead us to disaster if you don't stop me. Because you know, there is axiom in mathematical logic. From any mistake, wrong statement could lead to any statement. Wrong and right, any possible statement. So okay, anyway, let me be careful now. Nu C mu rho plus G mu sigma J nu rho. This we already wrote. Okay, this is, okay, actually, this is, I correct by myself. So we have I in front of this expression. Then also we learn with you that those guys, P mu, P nu, they commute. And now there is the last one between them, J and P. And this guy is not long. G nu sigma P mu minus G mu sigma P nu. You can see that this guy transform non-trivially, does not commute with J. And it's not surprising because, of course, we know that this is nothing else but 4 vector. And of course, even under rotation, momentum change, right? And under boost also they change, both energy and momentum. So because of that, we have this non-trivial. This is Poincare-Lie algebra. So by using all 10, now we have 10 generators, 6J and 4P, and considering this Poincare algebra, we get Poincare group, which just gives, given by the following. We consider this arbitrary parameters, real, this summation, this is what we already studied. Another one, what we studied very recently, today. So we have all those generators, and we could consider multiplication of this, and they act on function and so on. So anyway, this is what we call Poincare group. Right.
Why is it inhomogeneous?
Inhomogeneous because just translations consider like, this is word, first of all, right? Translations, you can call Poincare group if you dislike this. You know, it's historically. Homogeneous group, this is just initial Lorentz group with rotational and boost. And we consider in, yeah. I do not have good explanation, but I'm sure there was some historical. But it's language. You should not worry about that. So inhomogeneous, right, right.
So G, the metric. So
Right.
for a general Lie algebra, is there any, so because it depends on how you choose your G.
No, point is that G we defined, right, with you already, that any G here, G mu is diagonal, I'll 1, minus 1, minus 1, minus 1. Then it defines that G mu is this, 1, 1, 1, 1. So everything defined. So I put here this. We know what it is.
If I change my G, so do I still get the point?
Be careful in that. Yeah, you can, of course, change here and change here. Then minus minus gives plus.
I mean
And
the form of G.
yeah, sure, but be careful. That's it. Not just careful and that's it. Of course you can. Because this element, for example, it's equal, as I just said, you can write G mu rho, G nu sig. And this is same, and so on. But one should be careful. Just you should remember connection between them.
I meant actually making these numbers different. If these are not one.
Then you will not get Lorentz group. It will be something else. For example, if you consider curve space, gravity, we have different metrics, and Lorentz group is not there. It's only local. At each point you can consider.
This comes along with the definition.
It's in flat space, right? It's in Minkowski so-called space, right?
So I guess a follow-up is that does this algebra represent SO4 if that G mu was just a simple diagonal?
Okay. As I thought, when you consider this imaginary transformation for time, this Lorentz algebra present SO4. But you should consider imaginary types.
The two generators are slightly different.
Right, right, yeah, right. They're very, they look, we will be discussed, exactly. Yeah, go ahead.
How far is reducible group?
Sorry?
How far is then reducible group?
What you call reducible group? No, this is representation. No, the notion of reducible group, it does not exist. But you can consider reducible and irreducible representation. I a little bit right described here, tried, but yeah, some examples, right? Just in the beginning of lecture. But you see, there is no just, it's simple answer just in one line. You should consider any representation and consider, but those representation, m over 2, n over 2, they all irreducible. Those representation for Lorentz group. But I described, this is, for example, reducible, and so on. So you should, it's something like that. It's, okay, let's go. Now, let me note something interesting. Note, so let's consider this, actually, commutation relation. So now I discuss this, commutator P and J. Note that while just by using this, and now I substitute particular indexes, J, I, J, and took P0, derivative with respect to time, or x0. And this guy, I, J, 1, 2, 3. So it's connected with spatial component. And of course, it's 0. It's easy to check, right? With time derivatives, they commute. So while we have something interesting. Boost check this. So commutator of boost along I direction with derivative with respect to time, this is, and I, this is essentially energy operator. It gives momentum. It's not surprising because we know that under Lorentz group, under boost, energy and momentum mix, right? It's crucial. Again, I return to quantum mechanics. In quantum mechanics, this P0 is Hamiltonian, you will see. So you see, this guy with spatial 1 to 3 correspond usual angular momentum in 3 space. It commutes. So you could consider state with concrete angular momentum and energy. But this guy does not. So this guy cannot be used as good quantum number for the state with energy. This is different role of boost and rotation. Rotation gives us good quantum numbers angular momenta, which, because this operator commutes with Hamiltonian, but this not. So we usually do not use boost to describe physical states in quantum mechanics both and quantum field theory. Okay, so let me look, we still have time. Let me suggest, can we, because a lot of stuff, I am ready to teach, not until 12, by say 12:15. Is it okay? Will you survive? I will. But actually, it's easy to be a speaker sometimes than a student. Okay, so 12:15, right, go ahead.
For For there, if we have m and n equal 1, does it
Right.
mean,
1/2. This is I wrote.
No, just m and n 1, just 1 and 1, 2, sorry, m and n 2.
Oh, 2.
Does that have any physical representation?
So, okay, you consider 1. Actually, okay, I cannot immediately answer. I don't know, at least simple. But of course, you could consider particles with spin. So it will be something connected, right? 1. So what is it? Yeah, it's actually also symmetric, some representation, but tensor, but a little bit different. But yeah.
There is some particle referred to that.
Who?
There is some particle that connected that.
Yeah, certainly you can. You can consider some particle, it's tensor, so spin 2, something like that in this case.
Is it like graviton?
No, graviton, as I showed you, it's connected with this, right? Right.
So when you say J commutes with that, so if you think of P0 as the Hamilton, aren't you now making, so this is about just free power? Because if I have an Hamiltonian that's not rotationally symmetric, this cannot be obeyed.
No, you could consider, and we will consider in quantum field theory with interaction, which are Lorentz invariant and rotationally invariant, and so on.
Oh, but this is not a general statement. You cannot.
No, point is that if I'm considering generator, commutation relations valid for any representation. So it's always valid. When you believe that you have Lorentz symmetry or Poincare symmetry, those commutators you cannot change. Of course, if you do not have symmetry, then it's meaningless to consider that. But in all theories in which you have the symmetry, you should use. And there could be interaction, not just free particles. Okay. Now, let's discuss, and this is section 2.2 Peskin. But again, I don't follow exactly, but certainly I follow some stuff. This is classical field theories, not quantum. Okay, and I start from first classical mechanics, actually. Let me recall you. Lagrangian, there are two formalisms, Lagrangian and Hamiltonian. Okay, what we have in the case of classical mechanics. Okay, we have in the case of Lagrangian formalism, we have coordinate qi and velocities dot and I some finite number n, could be 1. And this guy, of course, as I said, velocity, its derivative with respect to time. We have action, which is written like integral action over time, dt. And then we have some function of coordinate and velocities, which is called Lagrangian. because it was introduced by French mathematician and mechanics Lagrangian. It could be very complicated.
Why is it not also a function of time?
Sorry?
Why is it not also a function of time?
Of M?
Of time.
Of time? Okay. We consider, you can consider this when there is explicit dependence on time. But we will consider the case when we just have coordinate. In that case, some things becomes a little bit different. But in this course also, we will mostly consider quantum field theories of this type when we have. So we consider this, but you could consider, of course. Okay, so we have this stuff. Let me put it, and let's go. Okay, I believe I used then everything. So one should now work. Now we use principle of least action. When a system we consider, okay, evolves, let me, from one given configuration. And this means we pick up initial, they equal value of my coordinate on time t1, right? Because my system from t1, t2, this is initial, this is final time. And we have this configuration to another. QE2, which is equal Q. So this is value at final time. It moves along the path I put quad because this is in n-dimensional space, right? But it's still path, of course. Maybe it's better. Path in configuration space. Configuration space is a space of all coordinates, n-dimensional space. For which S is an extreme, usually minimum. Okay, so you pick up path in that configuration space with fixed values at t1, t2 of q, evaluate this integral, and that path, which is realized in nature, classical nature, in classical mechanics, should give you usually minimum of s, but anyway, it's extremum. So this is axiom. There is no essential proof. It's assumed because from this principle one can get Newton equation, famous. This principle to famous Newton equation. Let us show how it leads to Newton. Sometimes in this Lagrange formalism, it's called Newton-Lagrange equation, or sometimes even Lagrange equations, but it's essentially Newton equations, but derived in very, very beautiful way. Okay, so what we consider is this. So we should find path which is extreme. What does it mean? So let's consider some particular path which corresponds to those n function of time. So this is our initial path. It includes all. And if we change a little bit this, this guy is small variation, right? The extremum condition, like in calculus, is that this is infinitesimal. So they are small. Infinitesimal. So small variation. This is extremum condition, delta S equals 0, like in calculus. First derivative equals 0. Yes, go ahead.
Usually minimum. So if there is physical equation.
Sorry?
You said that it's usually minimum. Can it be maximum?
Yeah, sometimes, but then you have bad system which is unstable and so called. Sometimes, yes, you can. But it corresponds some unstable move. You still get delta S equals 0, but this is a kind of unstable solution. And this studied in some direction, like stability. You should use Lyapunov theory and so on. It's true, but we will consider stable solutions, and then it should be minimum. But in usually extremum could be maximum. So delta S equal 0. So let's use this. Okay, so 0, delta S. And let us calculate delta S from S. This is our S. Calculate. This is integral from T1 to T2 dt. And here I change. This function depends on both coordinate and velocities. Plus of course, again, I'm considering summation over repeated indices I up to n. Okay, now let me rewrite second term in the following form. I do not touch the first one, it's okay, but I could rewrite this guy second as two terms. One, what is called full derivative with respect to time. Minus this is point. Okay, just check that this term, second term, where I considering variation of velocity, can be rewritten in this way. If you take derivative at derivative of the product, this guy cancel, and you will find this term as before. You can check by yourself this. So we have this, but this term we can integrate. We can integrate, right? So this is surface in mass called parallel. So this guy is given by this contribution dt you can calculate, and then you have this dl dq point I. This is answer after integration. Delta QE. And you considering you should substitute T1 and T2. But delta QE T1 delta QE T2 equals 0. Point is that we fix initial and final condition, right? We cannot consider variation of them, right? Because in our case, this guy is fixed at T1 and at T2. So we consider variation, but without changing initial and final conditions. So this guy is 0, and surface term is 0. Then we have actually, so this term you could ignore. No contribution of surface term. Okay, let me, it's not so busy. Then our variation of action is given because this guy is absent. So we have this term and second term. So it gives me this. Or I can write equality actually. This equal integral T1, T2, dt. And I have two terms. The first one, I did not touch it, and this term. And I could write even better. Let me, because those two terms have same variation, delta qi, right? So I put this guy outside square bracket. It depends on t. Okay, and this is equal 0, right? If we have extremum. We started from this, right? Look, we said 0 equals this. We came to this point. And we can consider it's arbitrary, right? Any variation in the bulk, not at the ends, then from this, because it's 0 for any small function, we get Newton equation. Newton Lagrange, or just Lagrange equation. And this is this. So we have system equation of ordinary differential equation of second order. Second order because we have velocity here, and then take one more derivative, and we have acceleration, right? So it's usual, like in Newton, we have second derivatives. So this is how we can derive, by using this principle of least action, famous Newton-Lagrange equation. Why I discuss this? Because we will use same approach in classical field theory. But in that case, we will get not ordinary differential equation or their system, but PDE, you will see, partial differential equation. Quantum field theory from a mathematical point of view is theory of PDE and their boundary conditions. This is actually, from the point of view of mathematics, is classical electrodynamics. You have Maxwell equations, which are PDE, complicated sometimes boundary condition. And if you are a Heaviside, great guy, who essentially was first to solve complicated PDE in Maxwell theory, and this was applied to get telegraph, for example, to get connection between telephone connection between Europe and North America. He found that it can be done. People did not believe in that. They consider that resistivity is inevitable, so sound will disappear in a wire. He found solution which showed no. If you are smart, if you pick up the right configuration, you are done. But he got 0 for that. No sense. Because, you see, he was a kind of guy, he did not care about application. It was recognized by other people, engineers. They just believed him. Mathematicians actually did not believe. But he was right. Okay. Now Hamiltonian. So we will heavily use this stuff. Now let me consider the case of Hamiltonian. It's a kind of review, what you should learn already, of course, for this course. We use both in quantum field theory. Now, instead velocity, you introduce momentum. And by definition, this guy is partial derivative of Lagrangian with respect to velocity I velocity. The Hamiltonian is the Hamiltonian is H, and this is definition, P in Q. Of course, everything depends on time. You should let me write this. Times minus Lagrangian. Of course, we have summation over I here. This is Hamiltonian. If you, from this, express all velocities through momenta, from this equation, Hamiltonian then depends on coordinate and momenta, not velocity. So velocities are replaced by momentum. Now we get the Hamiltonian equation. They are first order. Not second order. First order ODE. Let me write them. Okay, derivative of momenta is minus and partial derivative of Hamiltonian with respect to coordinate. And derivative of coordinate is with plus and partial derivative of Hamiltonian with respect to momenta. It's first order. Okay, I will not derive them. That actually it's not difficult. They follow from actually Lagrange equation. One can show. Maybe even Peskin considers this, but no, it seems he not. But anyway, it's easy just in any classical mechanics. And now we come to classical field theory. Let me just write a kind of introduction and we will stop. Now it's, so I need say 10, 15 minutes. Okay, so it's everything about mechanics we need. And now let me consider, say here, I start, and I will not erase it. It's already start classical field theory at last. First, I will consider Lagrange field theory, which is analog of Lagrange mechanics. The action is okay, S. Okay, let me, sorry, I should say this. For simplicity, we will consider one real field. But I will write in the end generalization, which is, I will use phi x. So theory just of one field. In this case, this guy, of course, depends on time, and this guy. And those x, they play of role of index I in classical mechanics. Okay, so we consider now some object, real object, which depends on time and 3 coordinates. And those coordinates play the role of those indices in classical mechanics. In this case, we had n degrees of freedom, right, connected with coordinate. In this case, we have infinite, of course, even continuum, right? So at each x, we can consider field. So this is non-trivial, of course, generalization. Okay, as before, we have this guy. And it's in field theory. It could be written in more convenient form. Now I will consider, let me write D for x, and this called Lagrangian density. Then we will consider example, of course. So we will consider some function, in general case, function of phi, which plays the role of coordinate qi. You see, q depended on I and t. Phi depends on x, which plays the role of I and t. And d mu phi. There is, of course, first of all, time derivative, and it plays the role of velocities, but also there is spatial derivative, and we will consider them. It's deformation. It's new object, right? So we can consider, so we will consider this. We will not consider higher derivatives, but actually now people study these field theories with higher derivatives. They're still not popular because they produce nothing at this moment, essentially, concerning application. But still, they could be, maybe at some point, useful. So this is Lagrangian density. Okay, so let me leave it here. And maybe, oh, okay. This is good. And we will stop here. And now next step, it's like in the Lagrangian mechanics, principle of least action, right? Zero. Again, we want to pick up, to find classical equation which pick up the right path, but now in this more complicated theory. Okay, so let's consider. I will not write now integral T1, T2. right? I mean, but you should remember, right? It's between, oh, it's another, actually. Because we still have, of course, some also boundary condition connected with spatial. So I mean, so it's four-dimensional integral. And very similar manipulation, but now I'm considering this guy L, define delta phi. Of course, everything depends on x here. Let me write once. Plus, this guy also depends on velocities or on four-dimensional grad d mu phi, right? So this guy is this. It's very similar. I still have. Okay, look what I wrote, compare with this. It has exactly this form. And now same trick. Second term will be rewritten by using some surface term. I will not touch the first term. It's okay. It's, you see, I meet already x. You should understand. Of course, everything depends on x. I just showed here explicitly. Now, plus this divergence term. And minus d mu oh, it's wrong. And this is this. Okay?
We don't need Romeo the second denominator. Do we need?
Here? No, we need. You see, I took derivative here of L with respect to d mu phi. Right, because you see this guy, look, it depends on this. So we take derivative with respect to d mu phi. It's simple. If, for example, this guy, say, includes this term, right? So then derivative of this guy is equal d mu phi. Okay, now the following. So what we have now, let me write. So we have actually initial condition and boundary condition in my region. Of course, it could be infinite all space, then boundary at infinity. But we have boundary condition and initial. It's like PDE, right? They are fixed. They could be Dirichlet type, Neumann type. Sorry, I do not have time, of course, to introduce you in that stuff. But they are fixed. What we will produce now, we will derive equation in the bulk. You cannot derive at boundary. There should be boundary condition made by our hands, by condition of the problem you consider. It could be Neumann, Dirichlet, mixed, Robin, and so on. But we want to derive equation in the bulk. So in this case, so we have this variation, right, of this guy. everything what we have, which depends on time and coordinate. So I will describe them as the following. Of course, because initial condition, like in mechanics, fixed, we cannot consider variation at T1 and T2. Right? Because of that, this surface term does not contribute at temporal endpoints, at T1 and T2, right? So derivative, but also I take delta phi t x, you cannot apparently see this, right? Okay, then sorry, I should. You can see this at least. Let me. Maybe I could write here. Delta variation phi t x when x is on the boundary is 0. I can take it. I'm not interested in, I have boundary condition. It's enough for me. So I do not consider. It's my right. Then, like in that case, if you consider this by using actually Gauss theorem, you could in 4-dimensional space, everything will be reduced either on boundary or at initial point. It's 0 because this guy is 0 there. Surface term do not contribute in this case. But in the bulk, delta phi, so I can kill this. Delta phi is arbitrary. Because of that, we can get equation, and it's called Euler-Lagrange equation. Two great mathematicians, one of greatest in history of science, Euler. Certainly you met this name in calculus, and Lagrange, also in calculus. Two giants. So from here, let me write, because it's fundamental, rewrite. Because this guy is absent, we get and only two, sorry. In last term. And from here, because this is 0, right? We get this local equation at each point x, time and spatial coordinate. This guy minus second term is equal 0. This is Euler, Lagrange, equation. PDE equation in general case, partial differential equation. Okay, so Newton did not consider PDE, by the way. It was enough for him to consider ODE. Okay, Euler-Lagrange. Yeah, I believe let us stop here. If you have questions, yes, please.